Projectile motion. Motion in two dimensions. When these cannons fire their cannonballs, physics can be used to predict exactly where those cannonballs are going to land. But before we do that, let's look at what we already know about linear motion. We just spent some time learning about that. So if the fuse burns down and it goes boom, ball goes straight up, falls straight down, but it was traveling in a line the entire time. But we know a lot about that. The definition of the average velocity is just the change in position. Final position minus initial position over how much time has elapsed was the definition of average velocity. And acceleration was defined as a change in velocity over time. With those definitions, we were able to come up with an equation that describes the instantaneous velocity in the horizontal direction as a function of time and acceleration in that same direction. And then we also developed an equation that would give us instantaneous velocity as a function of your position and your acceleration. And then the other equation was that the position was the initial position, the initial velocity in that direction times time, and 1/2 the acceleration in that direction times time squared. All right, and really everything boils down to these three equations there. And guess what? There are no new equations with projectile motion. These three equations are still going to be the three that we're going to use. In fact, we're going to mostly focus in on this one here and this one here. In projectile motion, things are still shot out of cannons and things like that, but instead of traveling in a line the entire time, they're going to curve and they're going to arc through the sky. They're going to be falling down and moving horizontally. So this is a little fountain where water gets shot like this and water gets shot like that, but it looks like it makes a very nice smooth shape, and that shape would be called a parabola. But it is very predictable, and we can understand exactly where that water is going to go. So if we have a smooth table and level, and we just rolled a ball along that table, as long as there's not any appreciable friction, the ball is going to move at a constant velocity along that table. If we hold the ball right here and drop it, it's not going to move at a constant velocity, it's going to move at a constant acceleration. The velocity is going to get greater and greater and greater. Now, the horizontal motion is going to be constant. It's not going to be accelerating. So if we take this equation here and the acceleration is 0, well, that term is just going to disappear. And we can predict its position knowing where it initially started, how fast it was initially going, and time. And then we can calculate how fast it's going based on how fast it was initially traveling. And well, in this example, the acceleration was also 0 because it was just moving along a horizontal surface. The light here would be like a strobe light. So let's say the room is completely dark and the strobe light flashes. When the light is off, you can't see the ball, but when the light flashes, we see the ball where it was at that moment. So we're just seeing the ball in these different positions. And we see that it travels the same distance every time. If we took a ball and held it right here and did the same thing, this time it's going to have constant acceleration. So same equation, except this time instead of just any old acceleration, we're going to be talking about the acceleration of gravity. And I'm not talking about x's or horizontal motion, I'm talking about vertical motion now, my y's. So I held it there, so it didn't have any initial velocity. It wasn't thrown up or it wasn't thrown down. The initial velocity in the y direction was 0, but it is accelerating, so that term is still going to be there. This equation here, it is accelerating, but again, it didn't have any initial velocity. So this equation without that term will predict where it's going to be at any time. This equation without that term says that whatever its initial velocity was, its instantaneous velocity is going to be the same, regardless of time, because time isn't a variable there. And then in the vertical direction, it is accelerating, so we can figure out where it's going to be. And it is accelerating, so we can figure out how fast it's going to be. But if we do our strobe light here, it's going to be going greater and greater and greater distances every time. So let's see if that ball is rolling along the table here, reaches the end of the table, but we take our gravity switch and we flip it off. Yes, a gravity switch. No such thing, but it would be interesting to see anyway. But if the ball reached the end of the table and gravity was flipped off, the ball would just continue traveling in a straight line at a constant velocity, traveling the same distance every time. So this is what the ball would look like if it did have horizontal velocity but no gravity. This is what the ball would look like if it had no horizontal velocity but it did have gravity. And let's see what it would look like if the ball's rolling along the table here, reaches the end, and it does have horizontal velocity and it does have gravity. It might arc down through the air like this and land on the ground, kind of bending as it goes. But the really cool thing here is that this ball, as it falls, would be in the exact same horizontal position as just a ball moving at a constant velocity. And we could predict its position. It was not accelerating, so that term disappears. And then its velocity, again, it was not accelerating horizontally, so that term is equal to 0. In the y direction, it is accelerating. It's going faster and faster and faster, so it's going farther and farther and farther every time. And so the same equation here, it is accelerating, but in this example, it wasn't thrown down, it wasn't thrown up, so it didn't have any velocity up or down. That term cancels. And similar with our velocity, it does have gravity, it is accelerating, but in this example, it didn't have any velocity. So these are the equations that could predict the horizontal position and its horizontal velocity, and its vertical position and its vertical velocity. And here's a device that I made to demonstrate the key concept behind projectile motion. A very stiff spring here on a pivot point. This little latch holds it in that position, but when I push that button and the latch comes undone, this whole bar here is going to swing backwards like this and thrust forward like this. So if this thing has the ground drop out from underneath it, that ball is just going to drop straight down. And this is going to push forward into it and throw it. So here's that device here. One ball is going to be just dropped, the other is going to be shot. And there it goes, and they fall, they fall, they fall, they fall. And you can see they hit the ground in the exact same amount of time. And that's because gravity is acting in the down direction. The ball that was moving horizontally, gravity had no different effect on it than a ball just traveling straight down. Gravity acts down, and it's going to pull things down regardless of if it's moving horizontally. And this is called independence of motion. The fact that it is moving horizontally is completely independent of what gravity does to it vertically. So if a kid is on the 10-meter board and just steps off of there and just falls straight 10 meters, he's going to hit the water in a certain period of time. But if they're running like mad like this and fly way out here and hit the water here, they're going to hit the water in the same amount of time. Because it doesn't matter if they're moving horizontally, gravity still pulls them down at the same rate. So what I would like to do is, there's a target we're trying to hit out here 4 meters away. And we want to calculate what should our initial velocity horizontally be. The biggest advice I can give you, and I think it's fairly safe to say that this is typically what you would do, and that advice is to find the time first. That's really important. I don't think you can go wrong if you find the time first. So the time it takes to hit this target is going to be the same amount of time as it just drops the 10 meters. So we're doing this vertically, and this term was 0 because we just dropped. We weren't thrown down or anything. And our initial height was 10 meters above the water, and we want to find out at what time our position is 0, if this is like the x-axis when y is 0. So we're doing this in meters, so we make sure our acceleration is in meters. It is negative here, so I would subtract 10 from both sides. I would multiply both sides by 2. I would divide both sides by negative 9.8, and then I'd get an answer, and then I'd square root that answer, but I would find that it would take 1.43 seconds to just drop straight down. But if we ran like mad off this thing and then fell straight down, it's going to take the same amount of time. So we've got 1.43 seconds to travel horizontally 4 meters. So this is our equation for position. It was not accelerating horizontally, it was just accelerating vertically. And I'm going to say I'm going to start my x-axis right here so that the x position was 0, no acceleration, so it is just this term here. We want to figure out when our position is 4 meters to the right, and we are traveling for this amount of time. What velocity should we do? 4.0 divided by 1.43, about 2.8 meters per second. If the kid runs off of there at 2.8 meters per second, they will land right in that target there. And I might suggest that 10 meters is a big jump. Don't land on anything but water, because water is pretty hard from that distance. Caution, this sign has sharp edges. Do not touch the edges of this sign. Oh, also the bridge is out ahead. Make sure you make that connection there. So let's say that we were racing down this thing in big steam engine here, and when we missed, or we saw the sign to avoid the sharp edges, but we forgot and didn't see that the bridge was out ahead. And I want to see, as that train comes racing along here at 27 meters per second, where is that train going to land in the water? The bridge is 14 meters off of the water, and this is our big key thing. I'll say it again, that this is independence of motion. The fact that that train was going crazy fast this way and lands in the water has nothing to do with how much time it takes to fall down. Moving horizontally is completely independent of moving vertically. And the other thing we need to reinforce is find the time to hit the water first. Okay, and that time is dependent on how far it's going to fall vertically. So it had no velocity in the vertical direction. It only had velocity in the horizontal direction. We're going to start 14 meters above the water, and we want to find out when our instantaneous position is 0 meters above the water. So again, we subtract both sides, 14 from both sides. We multiply both sides by 2. We divide both sides by negative 9.8. We get an answer, and then we take the square root of that answer, and we find it's going to take about 1.69 seconds to hit the water. 1.69 seconds to hit the water while it's flying out like this, or 1.69 seconds to just drop straight down. It's the same amount of time. So we've got 1.69 seconds to travel horizontally. Horizontally, we were not accelerating. We're going to say our initial position was 0, and we were not accelerating horizontally. So it's just velocity times time. horizontal velocity, and we've got 1.69 seconds to keep traveling that velocity until we hit the water. So about 45.6 meters away from the base is where we're going to land. And if you throw a life preserver there or get your boat ready to retrieve people, then you're in the right place. The next video I'm going to make is going to be how to calculate where to place each of these rings. So not just figuring out where the ball is going to land down here, but where is the ball going to be at a variety of different locations. So this ball is going to roll down the ramp, fly through the air, and we got to figure out where to place each of these rings. So that's a spreadsheet that will be my very next one that you can do. But once we do that, I've done the spreadsheet, I've calculated the position of all those. Here the ball goes flying through the air, hits every single ring perfectly, and then hits the target right here at the bottom. Projectile motion is pretty cool. All my examples so far, the ball was shot perfectly horizontal. And I said that in the vertical direction, it wasn't thrown up or down. It was just horizontal. But, a lot of times you throw things at angles, up or down. So this is where the previous video comes into play with vectors. That if I have an initial velocity, I'm going to shoot something up like this at some angle here. That velocity is kind of to the right and up. So there is a component of its velocity to the right. That would be our initial velocity horizontal. And there's a component of its velocity that's up. So there's initial velocity vertical. Well, if I know what the hypotenuse of that triangle is and the angle, I can say that the sine of that angle is opposite over hypotenuse. Okay, just using the trigonometric ratio sine. And I'm going to solve for this side because I knew the velocity and I knew the angle. This is just going to be the sine of the angle times that hypotenuse. So when we know this and we know this side here is just going to be the initial velocity times the sine of the angle. And then we can calculate this one over here. The cosine of the angle is adjacent over hypotenuse, and I want to find out what that adjacent side is. I multiply both sides by v sub naught, and this is what we get. So this is going to be how fast it's traveling horizontally. And I want to say it again, that this situation where we know the velocity and the angle, and we want to find components here and here, that situation is so common, we might start to get comfortable skipping that step and going straight to this step. The hypotenuse times the cosine of the angle gives us the adjacent side, and the hypotenuse times the sine of the angle gives us this opposite side. So if we take a ball and we launch it off at some angle here, the ball is going to kind of fly through the air there. But let's take our independence of motion idea again. Let's take a bright light and shine it straight down so that we see the shadow of the ball moving at various times. As that ball flies and arcs through the air like this, the ball is going to be in the exact same horizontal position as just something moving at a constant velocity. Okay, so there's no acceleration term there. And the velocity is going to be, and then the horizontal velocity is just this component here. Horizontal velocity times time plus our initial position would give us our instantaneous position. But we can calculate what this is by using hypotenuse times the cosine of the angle. And then if we have a bright light over here, as that ball flies through the air, it would cast a shadow over here. So the ball is going to go up, slow down, turn around, speed up, speed up, speed up, speed up. But the ball is going to be in the exact same vertical position as just a ball shot straight up and straight down. And in the vertical position, it is accelerating. And this time it did have some initial velocity. That initial velocity is calculated by this component here. So hypotenuse times the sine of the angle tells us what this is here. All right, now let's look. That was the equations for position. Now let's look at the equations for velocity. So this is a vector representing the magnitude and direction of its initial velocity. As that ball flies through the air, it's going to go slower, 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 and then faster, 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 faster. But each of its actual velocities has components. It has a horizontal component, and you can see that the horizontal component was the same all through the air. The vertical component is getting less and less and less and less and less, turns around and goes faster and faster and faster and faster. But whatever its velocity is at any instant here in the horizontal direction, it will be the same as what it was when it was initially shot. This velocity here, it maintains that velocity as it flies through the air horizontally. So we can calculate what that is going to be by finding the component here. And then the velocity in the y direction, it was accelerating, and so it's just initial velocity plus acceleration times time. This initial velocity is this component calculated with the sine of the angle times the hypotenuse. One interesting thing here, at the very top, it is stopped. The ball is stopped in the vertical direction. It's not going up or down there, but its velocity right there is entirely horizontal. That its actual velocity is the same as its initial horizontal velocity. Now in the previous video, when I was talking about vectors, I talked about special right triangles, 45, 45, 90, and 30, 60, 90, and those are the ratios of the sides for those triangles. But I also talked about a 3, 4, 5 Pythagorean triple. So if I shoot an object at 50 meters per second at a 36.9 degree angle, it's going to have 30 meters per second velocity up and down, or up, and it's going to be going 40 meters per second horizontally. That 30 meters per second, remember with a projectile motion problem, time is what you want to find first. So that 30 meters per second tells you it's going to be in the air for 6 seconds. It's going to come back to the ground 6 seconds later. Because if you shoot it up at 30 meters per second, 1 second later it's going to be going 20 meters per second, 1 second after that 10 meters per second, 3 seconds until it gets to the top at 0, 3 more seconds back to the ground. So our position is going to be the horizontal, where that's going to be way down here is the horizontal velocity times the time that it was traveling horizontally. So 240 meters per second. Sorry, just 240 meters. The seconds in the denominator and the seconds in the numerator would cancel. Now here, this is an interesting thing, that if this angle was 36.9, this angle was 53.1, this angle is 90. These two are complementary angles. So if instead I shot it at 50 meters per second, not at 36.9 degrees, but at 53.1 degrees, it has 30 meters per second horizontally, 40 meters per second vertically. That tells us it's going to be in the air for 8 seconds, 4 seconds before it comes to a stop, another 4 seconds to come down. So where is it going to land way out here? Well, it's traveling horizontally at 30 meters per second for the 8 seconds. It's going to land in the same position. Anytime you shoot an object at complementary angles, those two shoots would land in the same place. So if I shoot something at 15 degrees and I shoot it at the same speed at 75 degrees, the 75 is going to be going really high. It's going to be going in the air for a long period of time, but they will land in the same position. This won't be in the air for very long, but it's going pretty fast. So this blue one would hit the ground well before this red one, but they will hit the ground in the same place. This green one shot at 30 degrees, and this purple one shot at 60 degrees. Both of them would land in the same place. And then at 45 degrees, that's going to get us the distance that's shot the farthest. So if you're an athlete doing shot put or javelin, or you just want to throw something really, really, really far, you train and train and train to make sure that your launch angle is right at 45 degrees. That'll get you the furthest distance. So now we're going to shoot a basketball. It's a projectile, and we want to aim at hit a particular target. I want to say that this is a complicated problem, and maybe a little more complicated than you might typically see. With that, I don't want it to be afraid of this problem, and it's not that complicated, but just a few more steps involved. So I want to shoot this thing at some angle. I'm going to shoot it at 56 degrees at some velocity. So I want to figure out how fast should I throw it to hit a target that is 16 feet away. I'm saying he's about 1 foot behind the free throw line, and hit a target that's 10 feet up. The question is, how fast do we throw it? So, as typical, we want to find an equation that relates all the variables. So, horizontal position, initial horizontal position, this is the component that's horizontal, and time. So I'm going to say I'm going to start out at a horizontal position of 0, 16 feet away. Before I've done it in meters, so we have to be careful. We're using feet here. But when I do that, and then this is the velocity and time. The problem here is I have two unknowns. I don't know at what time it's going to land or how fast to actually throw it. So anytime I have two unknowns, I need two equations. Let's use that same equation for the vertical position. Okay, so this time it did have some initial velocity. That was up and down here. Sine gave us that. And I'm using negative 32.2 for gravity. That's feet per second per second. We had to use 32.2 feet per second because we're measuring distances in feet, not meters. So here's an equation. We started 7 feet above the ground. We want to hit a target that's 10 feet above the ground. And again, we have two variables, a v sub naught, a time, and then time here again. So we have two variables in this equation, two variables in that equation. Let's solve one of these equations for one of the variables. So I took 16 and I divided by the cosine of 56, and I also divided by t to get that variable by itself. Then I'm going to substitute all of this in for v sub naught. So when I put 16 over cosine of 56t in for right here, I'm going to get 16 in the numerator, sine of 56t here, cosine of 56t down here. T in the numerator and t in the denominator are going to cancel. And then a trigonometric identity is that sine of an angle divided by the cosine of the angle is the same as the tangent of the angle. And then I'm just taking half of 32.2. So we got 10, 7, all of that fun stuff, and then minus half of that. What's nice here is that I didn't have a t and a t squared, so I didn't need to use the quadratic formula. I can just subtract that, subtract this, divide by that, and then take the square root, and I get 1.134 seconds is when it's going to hit. But now that I know how much time it's going to take before it hits, I can plug it back into this equation to figure out how fast to throw it. So I'm plugging that into there, and 52.2 feet per second, 25.2 feet per second is how fast we need to throw it. Gonna land in the target. One last thing I need to remind you of is that if this is 56 degrees, make sure your calculator's in degree mode. that's an introduction to projectile motion. Opens up a whole new world of fun problems.